Um, whatever machine architectures you built, Intel was going to build one that was cheaper and faster for running Fortran. And you could say Fortran and C, because that's the conventional stuff. That's where all the profits are, all the existing code is. And so I switched from designing hardware to using compiler techniques. And from there was a short step into languages. And so I don't really regard myself as a languages guy. I'm a systems guy that do language and language-related tools.
I believe this year is the 40th birthday of C++.
It could be said so, yes.
So in 1979, you essentially added the idea of classes to the C programming language, and this created a new language that allows for a higher level of abstraction, but remains efficient and close to hardware. I'd love to hear the story of how this came about.
Yes. I'd just come to Bell Labs, and I needed to find a project, and I decided that sort of hardware design or high-level machine architecture was not going to be a really good thing to do for a long time. So I fell back on one of my other interests, which was distributed systems. So I wanted to build a distributed system. And I realized that to program such a thing, I needed two things. I needed facilities for writing really low-level code, memory managers, process schedulers, device drivers, and such. Fine. There was maybe 25 languages at the time that was good candidates for that, including C. And then I needed something to be able to talk about bits and pieces of a system. I want to say that this bit over here talks to that bit over there, and it talks in this particular way. There are languages that could do that, quite a few. They could handle abstraction. They could handle the definition of entities and precise specification of how they communicate. The problem was that languages that could do the high-level stuff couldn't do the low-level stuff, and vice versa. And so I knew Singular for the high-level thing, I knew C for the low-level thing, and others. And then I just put them together because that was what I needed. And this turned out to be quite successful. Friends and colleagues picked it up and used it for things I hadn't imagined. And after a while, I'd become a toolsmith, and I wasn't actually building distributed systems anymore. I was supporting users of what was first called C with classes, and then C++. One of the interesting things about this was that in the first week or so, 2 weeks, we got constructors and destructors, which is the basic support for resource management in C++. And I still think the only really complete way of dealing with resources safely and with minimal resource retention. And somewhere, sort of 6 weeks into the project, I decided I couldn't live without function argument checking, which C didn't have at the time. So, encouraged by my boss at the time, I just did it. And that was what became C's function prototypes. So I've contributed a fair bit to C. If you hear all of these C, C++ heated debates, people should remember I had lunch with Brian Kearney and Dennis Ritchie every day for 16 years, and we never had a fight. So const is something that I discussed with Dennis in detail. It was not that I didn't like C, it was that I needed something more than C.
So all of this was, about 40 years ago. Why is C++ still important today?
Yeah, that's interesting. I was lucky finding a problem that persists, and it's probably bigger today than it was then, and a solution approach that also scaled. So basically, there has always been a set of applications in the computing world that needs to use hardware really well, and for productivity and reliability needs to get away from the hardware fairly quickly, because it's complex software and you need to handle the complexity. So you could say C++ handles hardware and it handles complexity. That's the key. I was convinced in the early days not to build in solutions. I was building in tools for people to build solutions. So I didn't build in coroutines or concurrency support. I built in the tools for building coroutines and concurrency support. Mm-hmm. And this approach turned out to be really quite good, because it's easier to extend and provide alternatives, and it's used to this day. And the kind of systems we built are more dependent on complex software onto interesting hardware than it was in those days. All of these distributed systems, they talk to each other, and they have reliability constraints, performance constraints, power consumption constraints, heat emission constraints. Maintaining stuff is really hard. It might be down in a tunnel under the sea, or by a cable duct, or it may be on Mars. You have these constraints on the problem. And if you don't have a constraint on a problem, you can use any language, right? But there's a lot of problems that has constraints. Mm-hmm. So people use Python and JavaScript and things like that when the constraints on performance and reliability is not that great, say for experimentation with great large data sets and such, or for displaying pictures on a screen. But if you are doing the basic, say, communication between two parts of the system, and if, say, the two parts of the system is your brake pedal and your brakes, it's better be reliable, it's better be precise, it better be written by experts in that area. And there's so many problems in that category today. And my feeling is that the number of things we have that fit this category is increasing. So people talk about the Internet of Things. What are they? They're gadgets communicating with something else. Some of those gadgets people depend on for their lives. So performance, limited resource usage, say for batteries, and reliability, communication. I was lucky with the problem set, and I got off on a good. I started well. That was sort of luck, because there's no way anybody could have imagined back in 79 what the world would look like today. I mean, I'm looking at cameras. Each of them will probably have 4 or 5 processors, and they're probably programmed in C++ anyway. But that kind of gadgets is everywhere and increasing. And so the C++ community is increasing, not explosively. We don't see the exponential, but maybe 100,000 extra a year. It's still a lot of people. It's bigger than most communities that can show higher growth rates. But with 4.5 million programmers, it's hard to have a 20% growth rate.
I was reading about your PhD advisor, David Wheeler, and one of the things he's credited with is published papers in shelves collecting dust, which I take to be an emphasis of the importance of real-world impact over a purely academic focus. And I think of your career as being kind of in that vein. Do you see it that way, and why do you think that?
Let's see. First, David was a really great guy, and he is underrated because he actually didn't write very much. I think he became full professor at Cambridge and a fellow of the Royal Society for writing about 4 papers. He wrote part of the first book ever on programming. Mm-hmm. He wrote all the code and got somebody else to write the text. And he wrote the first program ever to run on a stored program computer. And he's the Wheeler and the Burroughs Wheeler transform. So if we ever ship code around using bzip2, you used his handiwork. He did some cryptography. He did some really good hardware work on look-aside caches and such. Lots and lots of stuff. But he didn't like writing. As a matter of fact, he has been described as the laziest computer scientist ever. He was willing to solve any problem whatsoever to avoid getting to do work. And so he has a string of excellent results, things built to his name, but he always dodged the writing. And so I wouldn't quite go that far. My publication list is sort of as long as my arm, because I think you need to communicate your results. But I never considered a paper the end result of a project. The end result has to be something that can benefit people. I mean, we can go back to my Danish background. So one of my favorite authors is he who does not plow must write. In other words, you either have to build concrete things or you have to sort of teach. And so I do both.
So what do you write and why?
When I write, it's always to communicate an idea. So I wrote my first book because Alejo, a friend of mine from Bell Labs, much senior to me at the time, told me I had to. I was bellyaching in his office that people kept asking these same questions all over again and again. It was getting tiring to answer all of these questions. He says, Bjarne, you have to write a book. What? Well, you have to write a book. You just write down all the questions and answers, and then you don't have to bother with them again. Great idea. There's only one snag. Once you answer all the easy questions, people start asking harder questions. And so I never got out of that again. But I did get into the habit that if you have a result, if you have an idea that actually works, you have to document it. You have to explain what's the problem, why is it worth solving, how did you solve it, what alternatives did you have, what evidence do you have that it actually works. And that's very much into the Bell Labs sort of ethos. You do something, you do it thoroughly, you do it well. It's not enough to solve 80% of the problem and get a clever paper and a fancy journal. I don't mind clever papers and fancy journals. I have some of them, but it is not the end product.
Mm-hmm. So with that in mind, I'd like to do a lightning round of a few of your books. I'll list a title, and I'd like to get the Bjarne Stroustrup one-sentence take on who should read it and why. So, A Tour of C++ Second Edition.
That's for people who are already programmers, know the fundamental concepts, and need a refresher on introduction to C++. It's 240 pages. It covers all of the language and all of the standard library, of course not in total depth.
Programming Principles and Practice Using C++.
That's for people who don't yet know how to program. So it explains the value of programming, and it starts from the beginning and works its way to the end. It was written because I was challenged to teach first-year students at Texas A&M some years ago. And basically half of the students had never seen a line of code before. The other half had maybe a couple of years of experience in high school. And after 3 months, you couldn't tell them apart because, well, some people have to unlearn things, other people have to learn other things. But this is a book for beginners. Experts find it a bit long-winded. Real beginners find it maybe a little bit terse. But it has worked at scale for a decade.
The C++ Programming Language, 4th edition.
C++ Programming Language, that's the book that tries to describe everything in great depth. And it's for either, if you're a professional C++ programmer, if you write it for a living, that's the book you want to read. That's the one you you want to have next to your screen when you program. For everybody else, it's more than you possibly could want to know about C++. Then you go to the tour instead.
So C++ today it's different than when you released it in 1979. It's even quite a bit different than when I first programmed in C++ in the late 1990s. What is it that makes modern C++ modern?
Modern C++ is just a better approximation of what I wanted back then. If you look at my early writings, and especially if you look at the design and evolution of C++, when I had some time to think about it and articulate my ideas, that was in 94, you can see a lot of things. I want better static type checking, I want better management of resources, and I want better compilation. This include model is not great enough and such. You go through fingers, and actually C++20 is by and large a much better approximation of that. There was things that I expressed a wish for quite early on that I just couldn't do. If you look at it, I wrote my first C++ compiler on a machine. The machine had 250K of memory. And I aimed for a machine that had a megabyte and ran 1 megahertz. I should be able to compile, generate good code that could be used on a machine like that, using a machine like that. I thought I was being quite daring because I didn't have such a machine till a bit later. And turned out I overshot the target. So when the PC came out and you only had 640K, it turned out that my stuff ran on it nicely. Hardly any other stuff ran on it nicely because people were used to using a lot of hardware inefficiently, and I was sort of a little bit obsessed with using the hardware well. I had to be because of the subject area that I was aiming for, the low-level system part. And today, it generates better code, it's cleaner, it's more succinctly, more precisely. You can express a solution more precisely in modern C++ than you could it then. But you go back and see, and the aim was to express the things precisely and correctly.
Interesting.
We're just better at it.
Things just keep getting better.
Yeah. Okay, there's some bloats, there's some features that couldn't be used, but there's another principle called the zero overhead principle, which is what you don't use, you don't pay for. Which means in some sense we can afford that bloat because it doesn't go into your source code or object code. If you don't use a part of C++, you could just as well pretend it's not there because de facto it isn't.
So you mentioned C++ 20, which will come out next year. What are some of the things that are coming in C++ 20? Okay,
so we have a feature freeze. We should have the full set of features for C++ 20 known. Furthermore, every feature that passed the feature freeze that will be in exists somewhere. So you may not be able to run it on all the major compilers, but there will be at least one compiler that has an adequate implementation so that people have been writing basically production quality code with it. So I love science fiction, but this is not science fiction. This is what exists somewhere, and somebody can use it. Somebody is using it today, and we should all be able to use it next year. I expect that full implementations of C++, as full as you can determine without being a tester, we should have, before the standard in 20, we should have it in Clang, GCC, Microsoft, and probably also for some of the embedded compilers. And so let's see, what have we got? Probably the thing people will notice most is modules. We finally get modularity. Instead of saying include a file and you get all the characters in and you have to pass all the characters and make it into a program, you can say import this kind of stuff and you get a pre-compiled, semi-compiled version in that you can use. and importantly, that semi-compiled version is the same, and if you include it 100 times, well, there's no particular overhead. Whereas if you include an include file 100 times, you have to do the work 100 times over. So I'm expecting to see 5-10 times speed ups if you make sure that your code actually is modular and uses those features. Modularity is really quite simple. If I include or import A and then do it for B, and then I turn around, do B, and then A, I should get the same result. Mm-hmm. If you have that property, you have much better what's called code hygiene than if you don't. And that can be used by the compilation systems to generate code faster. And I was a bit worried because this is a feature that you only get benefits from if you actually do a little bit of reorganization of your code. And a lot of people are very reluctant to touch code. Hey, it works. Why am I touching it? The answer is there's probably some residual bugs you can get rid of. Or in this particular case, here's the carrot. Would you like to compile 5 times faster? How about retiring some of your old compile servers, things like that? And that's the basic idea. So I explained this to some people with some fear. And the response I got was really interesting, was, yay, now we can finally clean up those messes we couldn't get permission to clean up before. Because, of course, the bean counters only see the beans to be counted. They don't see the technical debt they're building up. Mm-hmm. Whereas developers that actually look at the code know that they have a lot of trouble dealing with messy old code. And if you get modularity, better hygiene, you're actually saving yourself a lot in the future. And let's see, what else do we have? We have coroutines. Mm-hmm. So basically we can wait for a lot of things more easily. Mm-hmm. C++ had coroutines from at the end of the first year. I built the first coroutine library, and then that went out of use. And then in the noughts, 2005, thereabouts, all the languages started getting coroutines, and C++ was a bit behind, but now we're getting it. It's deployed in Clang and Microsoft, and I hope in the end of the year we'll get it in GCC. And so we can start organizing code in a slightly better way, especially for high performance I/O driven stuff, which we have a lot of.
You mentioned the standard.
I forgot my favorite feature. Typical. Because once it's done, you don't think about it. I've been using it for years.
Concepts?
It's concepts, all right. Finally, we get concept. We can specify the interfaces for generic code precisely. Mm-hmm. Remember what I said? I wanted precise specification back in the 80s. And when I decided to do templates to support generic programming, I wanted 3 things. I wanted something that was flexible to the point where it could do things I couldn't imagine. And I wanted to be efficient so that you could build a container that competed with C arrays. This is very hard because that's a very efficient feature, but very error prone. And finally, I wanted my precise specifications, and it took forever to get them. And now we got them. By the way, there's 0 overhead. If you use concepts to get precise specification, it doesn't cost you a cycle or a byte at runtime. And it gives you better debugging, better readability and such. And this actually is in GCC now, and it's been used for a couple of years, and so we know it works.
I'm excited for C++ 20.
It's going to be cool.
You mentioned the importance of C++ to engineering. One of the many awards you've won is the Charles Stark Draper Prize from the National Academy of Engineering. One of the things I noticed is that you won this prize last year as an individual. In the past, the prize has often gone to groups of engineers, so groups of engineers that developed LED lights, rechargeable batteries, cellular networking, LCD displays, satellites. But you won the award as an individual, so I'm curious how you think about your role as an individual creator of C++ together with the entire C++ community.
I mean, obviously, I'm amazed by the scale of the success of C++ and the scale of the acceptance. But obviously, I could not have done it on my own. And in my thank you speech down at the National Academy, I mentioned the community and the importance of the community. But I think to a very large extent, I came with some of the initial ideas, and I've been reasonably flexible to channel other people's ideas and such, rather than sort of my way or the highway, which I'm not very good at. And it is interesting. It's an engineering award. The engineers, the users of C++ for hard, demanding tasks are actually the ones that appreciate C++ the most. If you look at the C++ community, it's underrepresented in academia. In the committee, there's a few professors, but very much. If you look at the research literature, there's very little about C++, given its immense importance out there. And if you look at my awards, most are from engineering organizations. And I mean, the highest one is the Draper Award. They used to describe the Draper Award as what you give to engineers because we don't have Nobel Prizes. And that's sort of, woo! I was amazed.
Another award, or I guess honor really, is that your photo is on the wall at the Computer History Museum, which is just down the road from Udacity's headquarters in Mountain View, California. And the quote that appears next to your photo, and your photo is there because you're a fellow of the Computer History Museum, the quote you have is that design and computer programming are human activities. Forget that and all is lost. And I'm curious, why that quote?
Yes. I've never seen that plaque there. I haven't been there since it was put up. But the quote comes from one of the early versions of the C++ programming language. And I was looking at the way software is written. I mean, people look at a language and say, these are the language features, and this is what the language is. But really, that's not what it is. It's the code you write using those tools. And the code is written by people, and the people are part of organizations. And basically, if you want good code, you have to organize your people, educate your people, motivate your people in reasonable ways. People have to do good things in good ways so that it actually works. And I saw a lot of organizations that sort of thought they were building sausages or something like that. Apply a management structure and think in terms of pipelines and assembly lines and just, I don't care how it's done, just as long as you get the output. It doesn't seem to work. There's a high creative part in good code. There's a high degree of feedback when you do it well. That's back to the engineering. You don't just do a plan and then execute it with a bunch of certified morons that will do just the right thing. You actually have to try things along the way, rely on feedback, modify your system. Basically, good software is grown. The predecessor of a really good system is a working system. It's not a plan, not just a plan. And so I was encouraging people to look at the way software was written by people as part of looking at what's going on. So I was looking at software development as opposed to just language.
So one of your many accomplishments was to author the C++ coding standards for the U.S. military's Joint Strike Fighter. And I'm curious, what special conventions, considerations did you have to take into account when you're building an engineering project like that?
Let's see. Different projects have different constraints. Mm-hmm. This is one of the reasons we can't just say, this is the one true way of writing code. Mm-hmm. And if you are dealing with gadgets that can break and gadgets that are actually quite dangerous if you don't treat them right. You have to have higher reliability constraints. And so, in some sense, nothing particular special about those planes. But there's something special with any gadget where people's sort of lives depend on them working. I mentioned the brake before, and the fuel injectors. I've talked to people building fuel injectors for marine things, and then the flight controls here and the car controls and such. All of them has the property that you're under some hard real-time constraints. You squirt the engine, the oil, or you flip the wingtips. It has to be done just right at the right time. And also you have to be very reliable. And so those are the kind of constraints that was embedded in those guidelines. So for instance, the rule was that you don't use operator new after the engine is turned on. That is, you must do all your allocation before you start, because you mustn't run out of memory while flying. And in particular, if you have a general purpose allocator, you allocate and you deallocate. And if you do that, and if you don't do it just right, you get memory leaks or you get fragmentation. And you can get that even in a language with a garbage collector. But anyway, you can't afford a garbage collector because it's building an efficient garbage collector under real-time constraints, sort of a few microseconds, is hard. You don't want the garbage collector or your own program collecting garbage while the wingtips are supposed to flip. And so you have, that's one of the constraints that's pretty fundamental in all of that kind of software. And the other constraint that comes in a lot is that you have to respond in a reasonable time, which means that you have to use exceptions very carefully or not at all. We didn't have the tool infrastructure to be very careful back when that happened 15 years ago. So there's a ban against exceptions. I love exceptions, but you don't want the planes to fall out of the sky because you're cleaning up the mess slowly. So we had to make some compromises. But basically, most of C++, roughly with the exception of exceptions and free store allocation, dynamic memory allocation, heap allocation, it's the same thing. You can use in C++. It's predictable in the embedded system sense. And that's very important. It's actually interesting that we're building now a set of core guidelines for use of C++, which you can find on GitHub. Core C++ guideline or C++ core guidelines. I can't remember which one it is. Which has a lot of similarity to the stuff I did with Lockheed Martin, because the fundamental things, 95% of everything, really is the same. And one of the things I found actually in the bank, a lot of the special constraints on financial software are very similar to control systems. Reliability, speed, predictability. It's true for both domains. And in that, it differs from, say, web applications or games that has, or even Google searches. You can afford an error in those areas. You can afford a delay. But in control systems and in some of the finance stuff, no. So they're different. Similarly, reliability constraints are similar. So in a control system, people can die if you screw up. In a financial system, people can get ruined if you screw up. So you better not.
What are some applications of C++ or things you've seen people do with C++ that have really blown your mind?
I mean, there's so many things, and one of the not so nice thing about my work is that you can never see it. If you do good software, it's invisible. And I was always so envious about the graphics and robotics people. They gave such great demos. Whereas you write a compiler, and the only thing it ever says is you screw it up again, dummy. It says it in many different ways, and some of them helpful, but still, either it just worked or you don't see it. And same with the applications. So I think in terms of applications, it's usually the things you can see. So when I found the Higgs boson down at CERN, I knew they were using a lot of my language for things like simulation, planning, control, and such. So that was really cool, and I've been there. It's a great place. It's cool as in 2 Kelvin down there. The Mars rovers, of course, about 15% of the code on them are C++. But then the whole communication system and the deep space communication system is C++. And and then you see the cars, you see the cameras, and so I forget about it. I mean, there's Google, and there's Amazon, Facebook. Shouldn't be too proud of that probably, but it's there, and it's all over the place. My first approximation is you look at anything that has anything to do with a computer, sooner or later you'll find some C++ in it. I was talking to some people at Berkeley, and they were doing this Jupyter workspace that's notebook that's sort of basic to the data scientists, and it's mostly things like R and Python. But how do these things communicate? Down on the bottom sits a little C++ program that shifts all the data around for them. Because there you have to have performance, you have compactness, predictability, reliability. Down at the bottom you find some C++. And so that's my sort of basic guess. If you look at any computerized gadget, and you'll find something somewhere. Any system you'll find some C++ somewhere. And so sometimes I play a little game trying to find it, but most of the time I just assume it's there.
We use Jupyter notebooks to teach C++ in the nanodegree program, and
Ta-da!
So at Udacity, we hear a lot about digital transformation, especially from the companies that we work with. And digital transformation can have a lot of different meanings, but at a basic level, these companies we work with are trying to use software to make their businesses more effective and more efficient. And I'm curious, over the course of your career working with different companies and different partners, how have you seen this type of transformation done well, and what are some of the pitfalls to avoid?
It's such a general question that it's really hard to answer. I'm sort of more of an examples kind of guy. One of the things, and it's always easier to explain what you shouldn't do than what you should do. It's like, I never like to say the 10 Commandments because they only tell you what you shouldn't do. It doesn't tell you what you should do, right? But it's so much easier to say what you shouldn't. So one of the problems in large organizations is that you have stovepipes. People do the same thing over and over again. So getting sort of an organization that can build things that are shared across, so that you can have shared methodologies using the same kind of compiler, not falling behind with your tool chains, with technical depths, working on ways of exchanging data that so that it can get exchanged, because an organization that get it wrong, you have a data describing something here, you have a data describing roughly the same thing over here, and you can't actually share them, you can't send it there, you can't merge it, because they've got too many different formats, or in different languages, or their communications library can only talk to things of their own kind. You need to have a higher degree of sharing of formats, procedures, and code. And then if you only do that, you then found yourself you can't update it because too many people depend on it. So that has to go together with a constant effort to eliminate technical debt. Mm-hmm. You mustn't get stuck with, say, GCC 4.2 when the rest of the world is using 7.6.
Mm-hmm.
And so in an organization, you can easily get that kind of stuff because there's always a reason not to upgrade. The system works. Why mess with it? You might make a mistake. But unless you devote resources to that, it won't work. And if you go back to the third edition of the C++ programming language, I'm actually documenting some of the ideas there, mostly learned from AT&T, which had both the good bits and the not so good bits. It's a large organization. But I ran out of space was it the second edition? I ran out of space, so I took the software engineering bits out and stuck to the language. That's a pity, but there's 1,300 pages now. That's already a lot.
I know in the core guidelines, one of the things that comes up over and over again that you've written is consistency kind of trumps almost everything. Having a consistent style, a consistent naming convention.
That's right, and it's not easy. For starters, consistent style will not be your preferred style in all cases. Mm-hmm. You have your quirks, I have my quirks, and we like our quirks. And so, and similarly, people like their languages, they like their operating systems, they like their communication packages, and so an organization easily gets a lot of cultures that are totally separate. And if you go back to languages, what actually happened in the 60s, in the 50s and 60s, you got Fortran, which was really good for engineers and scientists. And you got COBOL, that was good for business people. And not only didn't the data formats work, they couldn't talk to each other because they had totally different vocabularies. And this is one of the strengths of traditional object-oriented programming coming out of the work on Simula, where they actually said, no, we have to have a common language, and then you can build your own abstractions in it. Mm-hmm. And that's an idea I picked up from Christian Nygaard, and it's very deep in C++. If you want something in your code, and you can talk about it as something, mm-hmm. a matrix, a communication channel, a module on a different system, you have to have a representation in the code as a type, as an object of a type that represents it. That is how you directly represent things. And that came out of Simula as an attempt to solve the stovepipe problems in the languages and the software of the 60s. Still a great idea.
How can learning C++ and developing that expertise help individuals who are trying to fill that talent gap?
C++ is a really flexible tool and a rather sharp knife. And if you get yourself into a situation where you have to use some new odd hardware, say the processors they're now building for TensorFlow, you need something like that, and you need people who can shift part of their knowledge from, say, general C++ into TensorFlow, and people who worked with the compilers, adding new optimization and targeting facilities for your for underlying it. So when there's this new field coming up, you don't want to train people from scratch. You want them to have a broad knowledge of a set of tools, and I'm talking about C++ here, which you can retarget for that. LLVM is the basis on just about any of the modern languages, because that's where they go. C++ is the key library underlying most of the advanced facilities. So C++'s role is as a general purpose tool that you can repurpose. And you don't know what the next breakthrough is going to be. You do not know what the next set of challenges are going to be. But my guess is it'll have something to do with hardware, it'll have something to do with complex systems, and that's where C++ shines. This is where you can get your educated people, where you can use the knowledge again.
That makes me excited to be teaching C++. I'd like to close with a couple questions, looking back at the breadth of your career. Over the course of 40 years of C++ and 50 years of engineering, Is there anything you would do differently?
Oh no. What would I do differently? I think luck has a fair bit of to do with it, and persistence. I mean, I worked my way out of a working class district in Denmark, which was really great place to be, and through places like Cambridge and Bell Labs. That's a combination of hard work and luck. And it's hard to philosophize in retrospect. What would I have done? Because I'd have to understand the field, and I would have to have the background, and I would have to be able to grasp the luck. I mean, there's this saying that says, the harder I work, the luckier I get. Or luck fortune favors a prepared mind. I think that's Pasteur or something like that. So, no, it's hard to second guess sort of the 1970s Bjarne. I know more than he does about his future. He knew more about his present than I now remember. I think in terms of switching to software and compiler-based things, I think I did the right thing. I think my deliberate bet on static type checking, I did the right bet. And so that was right. And I then think for every single feature and every single project, I think I could have done it better. But would I have known it at the time, and could I have done it at the time? I don't know. It's always working a bit harder, reading a bit more, knowing a little bit more at the time, learning a few more techniques, learning a few more applications, learning a few more languages, all kinds of good, but where do you get the time from? I was bringing up kids at the time. You can't just do your professional's job. You're also a human. Back to this thing, you shouldn't forget the human. And you burn out if you do nothing but work. And so a lot of the things that I would say I should have done, what would I have had to drop? It's like, when you're a curriculum, it's not hard to figure out what you should teach. It's hard to figure out what you should not teach because there's too much of it. And same with life. You have to have a life.
So the final question you touched on a little bit, but I want to dig a little deeper. You're one of the most accomplished software engineers in history. How did that come to be? You mentioned hard work, luck. Do you think those are the two main factors? Were there other factors, mentors that you had, intelligence? How do you think about the sources of your own success?
I mean, you need intelligence, but then lots of people have that. I mean, coming from my background, I was determined to do something useful. This idea that you must do something for others. You can't just write an academic paper or do crossword puzzles. Unless you get through and do something to help others. That has been a driver for me, and that comes from the childhood onwards, and motivated the hard work, by the way. And then mentors. David Wheeler was a really good person to talk to. He was my supervisor, my advisor at Cambridge, and every week I had a meeting with him for an hour or two, which is a talk. And it had the same kind of format. So here comes the bright young PhD student with some great ideas, right? Wow, I have ideas. And David says, yeah, Bjarne, it's not bad. Yeah, it's good. Actually, we almost did that for the ETSAC too. This is a dreaded word because that was from 56. And you realize that he was sort of 20 years ahead of you. And he says, but then we realized, and he's off to the races, and he spent an hour or two explaining alternatives, solution methods, and what actually happens in the end. So he was really good at explaining things in a straightforward way. And I could go and read the research papers later, but he could get the idea across much better. So that was important. The other person worth mentioning here is Brian Kernighan again. Talked to him a lot. The C++ was to a large extent invented on other people's blackboards, notably Brian's and a guy called Doug McElroy. Brian basically taught me to write technical stuff. He's the best technical writer I know. And Doug McElroy was another guy at Bell Labs. He was really, really good at understanding things. You go into his office because there's something you can't quite solve, and you explain it to him. When you're finished explaining to him, you understand it better because you've had to articulate it to him. And then he plays it back to you, and it seems that he understands it better than you do now. Really great guy. And so he comes into this kind of category, close to being a mentor. But I'm not sure, I don't know if they thought of themselves like that. I mean, it was David's official job was to mentor me, but he just liked explaining things.
Well, thank you very much, Bjarne Stroustrup. It has been an honor, and thank you for the C++ programming language.
Thank you.
4 million C++ developers around the world are grateful.
Great. Thank you. Thank you.